Good morning. In today's lesson, we will go over a couple of examples, 2 examples to be more precise. And the goal of this lesson is to put together some of the stuff we learned already. So for the first part, I'm going to do another non-homogeneous problem involving the method of variation of parameters, which we learned last time. And the second example will be a mixture of the 2 techniques we learned on how to deal with non-homogeneous problems. So both problems will be non-homogeneous. One thing I want to get out of this lesson is to understand that these techniques we learned often do not appear by themselves in a given problem. So some problems, depending on the way they look like, can be solved via combinations of techniques we learned. So one of the things you have to aim to understand as we move along is if you see a boundary value problem and you spend enough time, as you should, in analyzing the type of the problem, then you should anticipate which techniques are suitable to deal with some specific issues for the problem itself. So, for example, if I look at the problem here that I wrote already, so take a moment to write it down. Again, let's take our time to analyze what it says, what it represents, and to anticipate some of the things we have to do. So basically to lay down the plan of attack. So it's a linear boundary value problem. It's a heat equation, right? As we can see from the dependent variable, u partial t on the left, for u partial x twice. It has homogeneous boundary conditions of Newman type. So basically this condition, because it's given in terms of the partial derivatives with respect to the space variable, so this means that the rod, which is described by this equation, the heat that flows into a one-dimensional rod, these are of Newman type, Newman conditions, which means from a physical perspective that the endpoints or the end sides of the object are insulated. So there is no heat flow across the left and the right hand point. And the length of the rod is 1, right? So x is between 0 and 1. Then we have an initial temperature given by x squared, right? So u of x0 equals x squared. Homogeneous Newman problem, that's the initial condition. Non-homogeneous problem overall, though, because we have this extra term, which, like I said before, it may denote internally generated heat as time goes on. So it's a non-homogeneous problem because of this, but the boundary conditions are homogeneous, and they are in terms of a derivative. Now, why that's important? Well, first of all, the type of boundary conditions already gives us some clue of what type of Sturm-Liouville problem we're going to have to deal with. So it's the Sturm-Liouville problem that will lead to the eigenfunctions in terms of the cosine functions. So that's useful to know beforehand. On the other hand, because of the fact that the non-homogeneous term is depending on t, then we have to use the method of undetermined coefficients, the method of variation of parameters in dealing with the non-homogeneous problem. So at this point, you may want to look at the notes from the previous lesson and remember what we talked about. Basically, the non-homogeneous term, you should think of it as a product of a function in t and a function in x. So this is how you should view this t here. Again, that's very important because remember, in the process of solving that problem, the variation of parameters, you will need to produce the appropriate Fourier series for f of x and for x squared. And in my case here, f of x is just 1. Okay, so even though it's a constant, you still need to write it down in terms of an appropriate Fourier series. A Fourier series in terms of the eigenfunctions. So at this point, let's see actually what eigenfunctions do I have to deal with. Now, remember, if you were to solve just the homogeneous part of the equation, and we're going to skip some steps here, okay, because you should know already how it goes from here, right? So if I were to do the separation of variables for just the homogeneous part of the problem, and if I do the separation correctly, right? So after separating the variables, then the Sturm-Liouville problem that you end up with, and again, take a moment, pause, and do the steps on your own if you don't remember where it comes from. The Sturm-Liouville problem will be x double prime plus lambda x equals 0, with the boundary conditions x prime of 0 equals x prime of 1 equals 0. So in this case, the eigenvalues and eigenfunctions, unlike the Dirichlet condition, 0 is also an eigenvalue with the corresponding eigenfunction equal to 1. And the other ones are n pi squared with the eigenfunctions cosine of n pi x. Okay, because the interval is 0, 1. So if you remember, that means the Fourier series has the extra term on the outside, given by a constant. Which means in the process of using the variation of parameters, because remember now you have to take basically a linear combination of the eigenfunctions coming from the homogeneous part, with the coefficients now being unknown functions of t. Okay, so that's the essence of the method of undetermined coefficients. Oh, variation of parameters, I keep on saying. Undetermined coefficients from a different topic. So variation of parameters. So now you take u of xt, the solution of the original problem, to be a linear combination of these eigenfunctions with coefficients to be determined. So the coefficients of the eigenfunction 1, let's call that a naught of t times 1, and the rest of them can be part of a summation. So from summation from 1 to infinity, a n of t cosine of n pi x. So if you look at the previous example, we didn't have this external part here out of the summation, because in the case of the Sturm-Liouville problem, which leads to sine functions, the 0 is not an eigenvalue. So in the case of Dirichlet condition, when you had x of 0 equals x of 1 equals 0, you only had strictly positive eigenvalues, n pi squared in this case, and the sine of n pi x. In the case of these conditions, you also have the 0 eigenvalue. So you have an external part here outside of the summation. Other than that, the whole technique you will see unfolds pretty much in the same manner as in the case of Dirichlet condition type. So before we plug in this function here into the problem, remember, we're going to have to get f of x, which is 1 in my case, the coefficient of t, now in terms of the same type of Fourier series, and x squared as well in terms of the same Fourier series. Now, from the table, look at the table of the cosine series. We get that x squared is equal to, on interval 0, 1. So x squared is equal to 1 over 3 plus 4 over pi squared, summation from 1 to infinity, minus 1 to the n over n squared cosine of n pi x. We're going to save this for later. The 1 to be written in terms of a cosine series, sometimes this is kind of confusing, but you will see actually this leads to a trivial cosine series. You might be surprised that in the table, if you look at the table of Fourier series in our book, there's no series given for 1. There's no cosine series given for 1. Whereas if you flip the page, if you turn the page, there is a sine series for 1. The reason is because the cosine series for 1 is actually trivial. It's 1 plus 0, 0, 0, 0, and so on. So let me illustrate why that's the case. Because by the way, let's say you're faced with this problem and you don't have a table of series, right? Then you should never forget the formulas of obtaining the Fourier coefficients. So for a given function, so for a function f of x, the cosine Fourier series on the interval 0, 1 is given by, this is basically just a recollection of the definition of the Fourier series, right? So it's given by a naught over 2 plus summation from 1 to infinity an cosine of n pi x. This is just all the way back to our first topic when we learned Fourier series. And remember, the reason we put these extra coefficients in the form of a naught over 2 is because this way the formula for the coefficients is going to be the same. Namely, an is given by 2 over c. Now c is the length of the interval, so in my case 2 over 1. The integral from 0 to 1 f of x cosine of nx dx. All right, so that is, again, if this comes out of the blue, because it's been a while since we used the definition of the Fourier series, just go all the way back in the beginning of the class and look at the formula for the Fourier coefficients on the interval 0c. So these integrals actually are very trivial if f of x is a constant. So take a look carefully here. If n is greater than 0, so if n is 1, 2, 3, and so on, if I replace f of x with 1, this was n pi x, I'm sorry, so cosine of n pi x, because it's interval 0, 1. So cosine of n pi x dx. This is just 0 because the antiderivative is 2. This is minus sine over n pi, right? So if I integrate that, it's sine of n pi x over n pi between 0 and 1. But this is 0 because if I plug in 1, sine of n pi is 0. If I plug in 0, sine of 0 is 0. So all the Fourier coefficients are 0 if n is equal to 1, 2, 3, and so on. All the coefficients are 0 for n positive. I have to treat the case n equals 0 separately, because remember, this won't make sense if I divide it by 0. Again, remember, in some cases, you will need to do that. Some coefficients need to be computed separately, because otherwise, this integral, this antiderivative won't make sense. So a naught, going all the way back to the definition, that's going to be 2, the integral from 0 to 1, again, 1 times, now it's cosine of 0 pi x, but that's just 1. So that's just 1 dx. And the integral of 1, of course, it's x. And a naught is 2. So f of x, which is the constant function 1, as a Fourier cosine series is a naught over 2. So 2 over 2 plus summation from 1 to infinity, 0 times cosine of n pi x. Which, unsurprisingly and somewhat unsatisfying if you want, 1 is basically 1 plus 0 plus 0 plus 0 dot dot dot. And you may find this actually kind of silly, because I mean, couldn't have told beforehand. So I mean, yeah, you could have guessed beforehand without going through this definition that the cosine series for a constant function, it's actually trivial. So all the 0 coefficients except the first one, which is the function itself, in my case 1. But this is what you do if you forget this little trick and if you don't have a table of formulas in front of you. We're going to keep it in that form though, because it's very important when we use the method of variation of parameters to match the coefficients carefully, left and right. So let's move on to the second page, and I'm going to copy again the problem and in this series that we wrote so far, and then proceed with plugging in this format into the PDE. Let's make it actually a second part on the lesson so that I'll write everything on the page before we start discussing the next steps.